Lesson 4 is applying properties of definite integrals. Some of what you're going to see, we're still working with finding area under the curve. We're still working with some of the same pieces, but it's more what kind of properties can we work with. I showed you a little bit of a property when I talked about flipping the upper and lower limits. Okay, so notice it says in this section, we move beyond finite sums or just rectangles and explore what happens in the limit as terms become infinitely small and the number of rectangles approach infinity. We'll look at some geometric functions that may contain negative values below the x-axis, as well as positive values above the x-axis and 0. We've already dealt with negative area, but it mentions here dealing with negative area. At times we'll integrate functions that go below the x-axis, thus negatives. A few pointers for when this happens. The area below the x-axis counts as a negative area. And when we talk about the total area from value A to value B for some curve, it's really what they define as a net area, because as you are combining that area, that total below the x-axis could be a negative. So the total below the x-axis and above the curve is subtracted from the total area. So just the idea, the net area, that you're adding and subtracting as you go. Okay, it's not just all adding. We have some integral notation. Okay, you've already seen a little bit of this integral notation. Okay, when I read this notation, what you'll usually hear me say is something along the lines of the integral from a to b of f of x dx, or f of x with respect to x. Okay, that dx tells us what variable we're working with, so with respect to x. And I cheated here. Let's see if it's going to work. I filled in this page. So I don't have to write it all out right now. I wrote it all out during homeroom. Okay, so the definite integral from a to b of f of x with respect to x. Okay, but we also often just say dx there at the end. Okay, the definite integral from a to b of f of x with respect to x. And remember to go lower to upper limits when you read that, because if you're reading it, someone might not have the paper in front, have the graphic in front of them, so they need to know, and that's universally you go the lower limit to the upper limit. Okay. We've got some names here to fill in. This curvy sign is our integral sign. There might be a more fancier name for it too, but integral sign is what we usually refer to it as. The A and the B. So the A is your lower limit of integration. And when we read it, that's what we read first. And then that means your B is the upper limit of integration. Okay, you're going from lower limit to upper limit. F of x, well, it's going to be the function we're integrating, the function we're working with. It's also called the integrand. Okay, excuse me. It's also called the integrand. It also represents a derivative. With the d of x, we've talked about that before. It's similar to delta x, where it represents the width of the interval. But when we get in this fancy, when we have an actual function here, it just represents that you're working with it's with respect to x, that we are integrating the variable of x. Okay. And then lastly, the blank at the bottom. This whole thing is a definite integral. Now, eventually we'll talk about something called an indefinite integral, but this is a definite integral because it has the boundaries a and b. Okay, so when we talk about an indefinite integral, that'll be a slightly different situation where you won't necessarily have the a and b values. Okay? And then the definite integral can be used to determine blank. Well, there we're talking about our net area. Okay, it's area under the curve. So net area, that is not the button I meant to hit. So net area or displacement, it's that net area displacement bounded by the x-axis, the curve, so the function f of x, and then your limits, or the vertical lines from x equals a to b. Okay? That x equals a to b. They say vertical lines there because sometimes the graph doesn't end there. That's just where we're chopping it off, and that's where we're stopping. Okay. Turn the page when you're ready. And in a way, we're still doing some of the same stuff we've been doing. Okay. On this, they give us this graph with parts A through, what is it, L? They ask us to use this graph to evaluate each of the following. Some information. Note that the graph of f of x consists entirely of line segments and a semicircle on the interval from -8 to 13. So with the exception of the semicircle, you assume that everything else are straight line segments. Okay? Now, A, the integral from 0 to 7 of f of x dx. So the integral from 0 to 7 of f of x with respect to x. What do you think? What are we doing? Area of a trapezoid? Yes? Because we're going from 0 to 7, so it's area of a trapezoid. What about this trapezoid?
It's a height of 4, and base of 3 and 7.
Okay. I'm with them. 1/2 times 4 times the 3 plus 7. So that area is going to be 20. I guess I could fill in my work here, couldn't I? I already put my work over there, but fill in your work wherever. Okay, that was easy enough, wasn't it? What about B? The integral from 0 to 13 of f of x with respect to x. What do we need to think about for 0 to 13? Okay, or part of it's negative, yes. So we already have the 0 to 7 that's going to be 20, right? And then what? We've got to figure out the 7 to 13. One half times a height of 3 and bases of 6 and 3.
27 over 2.
Oh yeah, because I did my math wrong. I was multiplying 6 times 3 in my parentheses, and I'm like, what? Okay, yeah, 6 plus 3 is 9. 9 times 3 is 27. So 27 over 2, 13 and a half. So this right here is 13 and a half. And what do I need to consider, though? Negative 13.5. And 20 minus 13.5 is going to be 6. 6.5. Okay. What about C, the integral from -6 to 0 of f of x with respect to x? Okay. So -6 to 0 is this semicircle here. 1/2 pi r squared. So 1/2 times pi times what's my radius? 3. Yes, because we've got this circle. It's 6 across here if it's a semicircle, so that means the radius is 3. So 3 squared is 9. Half of 9 is 9/2. And so 9/2 pi. And what do we need to consider here? This is a negative 9/2 pi, isn't it? Or negative 4.5 pi, you know. I just find it, I don't know, for whatever reason, it seems weird to me to use a decimal with a pi symbol. More natural with fraction, but it is what it is. Okay, good. D, the integral from 3 to 3 of f of x dx.
0.
Yes? Because if you're going from 3 to 3, hopefully that makes logical sense now. That's going to be one of our rules. It's one of our properties. But to go from 3 to 3, you don't move. So that is just 0. Okay? What about the integral from 7 to 0 of f of x with respect to dx, or with respect to x? Because what have we already done? We've already done 0 to 7, yes? And when you reverse those, it's the negative of that. So the official property here is the negative of the integral from 0 to 7 of f of x dx. We already found that to be 20, so this is negative 20.
Wait, why are we doing that? Oh, 7 to 0. Okay.
Are you there?
Yeah.
Yeah, you always want the smaller boundary on bottom when you're actually doing the solving here. Okay. What about F? Have we done 4 to 10 yet?
Mm-hmm.
Not exactly, have we? Now, this is the integral from 10 to 4, so what am I going to suggest here? Yeah, the negative of the integral from 4 to 10 of f of x dx. All it means is that whatever we come up with for our answer, it's going to be the opposite of it. Now, from 4 to 10 means I'm going from here to here. I don't have either of those informations, do I? So we've got to find them. A few new trapezoids? So what? The trapezoid from 4 to 7 is 1/2 times 4 times 3 plus 1, if I've done my math correctly. So this section here is 8. That's just that section there. And then the bottom piece, 1/2 times 3 times bases of 3 and 2. I've got 15/2, or in other words, 7.5. And what do we have to keep in mind? That is a negative 7.5 in that little section down there, isn't it? Okay, so it's going to be the negative of, what are we going to have to do? We had 8 for the positive section, 7.5 for the negative section. So 8 minus 7.5 is going to be a half. And the opposite of it means we're going to have negative 1/2 or negative 0.5. Okay. G, the integral from negative 8 to 13. The whole thing?
Yeah.
Okay. You're going to be looking at the whole thing here. Now, what's the piece we don't know right now?
Negative 8 to 6.
And negative 8 to 6
4.
is a triangle. 1/2 times 2. Yep. Height of 4, so half of 8 or 4. So what do we have here? We're going to have 4.
Plus 28.
Plus what?
28. No, just plus 20.
Just plus 20. I know. My thing's a little confusing there, but you have to, yeah, mark it better or know what you did. So, okay, so he's saying 4 plus 20. Then what?
Minus 13.5 and minus 4.5.
Yeah, I just realized I know I'm going to have 9/2 pi. No, I did mix. I mixed decimals and fractions a little bit, so because I'm going to keep it as 9/2 pi. Okay, so 4 plus 20 is 24. 24 minus 13.5, 10.5. So one answer here, 10.5 minus 9/2 pi, right? We're combining a decimal and a fraction, so I don't think you'd ever see that on a multiple choice scenario. Okay. What is 10.5 as a fraction? It's 10.5 improper. If we change 10.5 to a mixed number, it becomes
11/2. No. 20.
10/2? No, that's not right. It's like
21 divided by 2.
There we go. 2 times 10 is 20 plus 1, 21/2. Okay. My brain was getting confused with you guys. I don't know what my excuse is, but it was just getting confused too. So then that is 21/2 minus 9/2 pi, which at that point, if you're going to do that, there's one other way you could put it is those have a common denominator, don't they? So you could also see 21 minus 9 pi over 2. Okay, guys. Ready for H? Okay. Now, I always have to go back and, as we talk about f prime of negative 6. So what is this graph? This graph is f, yes? So you're looking at a graph of f. We're being asked the derivative of f at negative 6.
It would be negative.
So the derivative of the graph at negative 6. So we do the derivative of the graph. What generally is the derivative? We talked all first semester. When we talk about derivative, it's the slope of the tangent line. Okay? So, if there's a curve, you know, you can draw in the tangent line. If it's already a straight line, it's just the slope of the straight line there. What's going on at -6?
0.
Not 0. What kind of point is there?
Sharp cusp.
Sharp point, cusp? What do we know about the derivative at a sharp point or a cusp?
D.
It does not exist. How quickly we have forgotten first semester, right? So the derivative at -6 does not exist. You can either say D and E or undefined is the other piece I have written there. What's the reasoning? Because there is a cusp, hard point, sharp point, etc. Now, I will say, because there's a derivative, we were looking for the slope at x equals -6. That is what we are looking for. The slope just wasn't happening. Okay. Ready for I? That is the second derivative of f when x equals 6.
Concave down.
No. However, you're thinking on the right track. In that second derivative, we need to talk about concavity, but it's not concave down. So since it's a straight line at that point, we can't talk about concavity in that sense because it's a straight line.
So it
It's not curved one way or the other.
does not exist.
It does exist, it just has a concavity of 0. Okay, now, what I was going to take you through, and you guys figured out that you need to go for a concavity, just to kind of, you know, if you're just asked f of 6, no derivative, what is f of 6? F of 6 is 2, the y value, right? If we're asked f prime of 6, so the derivative at 6, that would be what?
-2.
It's the slope of the tangent line, which this is a straight line, so exactly it is the slope of that line, and the slope of that line is -2. So now, you've already done the slope of a straight line at that point. It'd be one thing if, you know, we were trying to, you know, like if we had to do a tangent line to find the first derivative and there's actually a curve here, then we could talk second derivative. We could at least talk if it's positive or negative. But when that's already a straight line, the derivative of that is going to be 0. Because there is no concavity there. Okay. And a 0 second derivative, it could mean a point of inflection. It could mean some critical point. It just depends. So. Okay, we're pulling out from some first semester stuff here. We can't forget first semester that quickly. Okay, let's look at J. Average rate of change in F over the interval 0 to 5. average rate of change.
You do that.
Yeah.
Because average rate of change is AROC? Yes? Okay. Average rate of change is AROC. So you're doing f of 5 minus f of 0 over 5 minus 0. F of 5 is 4 minus f of 0, which is 0, over 5 minus 0, I think. Okay. So 4/5. Okay. Let's look at K.
Okay.
True or false? The integral from 0 to 2 of f of x plus the integral from 2 to 4 of f of x equals the integral of 0 to 4 of f of x.
True.
Why?
Because it's all the same, it's just splitting them up.
It's all the same, just splitting them up? Okay.
Yes, I agree.
And why do you agree?
With what he said.
If he said, okay.
If you do 0 to 2, it's 4.
Uh-huh.
If you do 2 to 4, it's 8. If you do 0 to 4, then it's 12.
Okay. So Augie actually checked the math there, right? Logically, it makes sense, doesn't it? Okay. This is true. This is one of the properties we're getting ready to learn on the next page. Okay. And it's an important property, but it's the idea that, yes, most of the time you can take like an integral from 0 to 4 and you can split it into pieces. So you take the area from 0 to 2 and the area from 2 to 4 and you add them. Yeah, it should be the same as the area from 0 to 4. Okay, so the key is that your upper limit on on one of them matches your lower limit on the other. Okay, those limits have to match. They have to be joining next to each other essentially, but then it works. Good. Okay. Over which values over which values of x is f of x not differentiable? So, I'm going to say at x equals, which values of x is it not differentiable? We've already got one we talked about earlier.
-6.
We already talked about -6. And why was -6 not differentiable?
Because it was a sharp point.
There's a sharp point, a cusp.
So would it be every time that it touches the x-axis?
Not because it touches the x-axis.
Then cross?
No, because this one isn't not differentiable because it's at the x-axis. It's because it's a line and a circle, and that's not a flowing point, so to speak.
So could we do like 0 and 2?
Okay. So 0, it happens to be the x-axis, but it's not because it's crossing the x-axis. It's because it's considered a sharp point. 2 is considered a sharp point. 5 is considered a sharp point. 7 is, and the reason is those two lines, they almost look they are continuous, but they almost look flowing, but they have different slopes there, don't they?
Yeah.
Okay. And then 8 and 11. Okay. So, -6, 0, I don't even know what all we wrote at this point. 2, 5, 7, 8, 11. Okay? Okay. Moving on to the next page a little bit. And we have some properties at the top of this next page. Okay? And several of these properties now at this point are going to seem familiar because we've essentially already learned a lot of these properties. I'm not going to say all of them, but a lot of them. So, the definition of the definite integral of f on the interval to a to b specifies that a is less than b. I've mentioned that, right? So your lower limit needs to be the smaller limit. Now, however, it is convenient to extend the definition to cover cases in which a equals b or a is greater than b. So, number one, we've already talked about this. If f is defined at x equals a, then the integral from a to a. When your upper and lower limits are the same, it's going to be 0 every time. Okay? If f is integrable, integrable, doesn't sound right, but whatever, on the interval a to b, then the interval from b to a, okay, so this is where, assuming a is the smaller one, you flip it, and it's the opposite of it, so the negative of it. Again, that's one we've already used, haven't we? Okay, I've already introduced that one. 3, this is the one we just introduced on that true-false question. If f is integrable on the 3 closed intervals determined by a, b, and c, then the integral from a to b can be broken up from a to c and c to b. And so that would be the idea that c is somewhere in the middle of a to b. And so you can break it into those pieces. The same one we just did with, what was it, from 0 to 2 and 2 to 4. Okay, same idea. And then some properties. These are ones we haven't really used much quite yet. Number 4, the integral from a to b of k times f of x. So k is a constant here. So the idea that this k, if it's a constant, it can be moved outside. It's helpful to move it outside when we actually start integrating things. It's one less thing you have to worry about when integrating. And so a constant can be moved outside. It just makes the math a little easier. Okay? If you're integrating a constant, we'll have a rule when there's actually a function here, but if you're integrating a constant from a to b, then we have this rule here, that it's the constant k times the difference of the limits, so times b minus a. Once we know how to integrate that, you won't really have to think about that rule, but it is helpful for what we're doing on these next couple examples. And then 6, I feel like we've already done this, but the integral from a to b of f of x plus g of x or f of x minus g of x is just saying you can break it into 2 separate integrals. And that's kind of what we've been doing on the area, right? If it was the integral from negative 13 to 7 or whatever, we broke it up into the pieces. And that's, if there's different functions, you can break it up into different functions, okay? Now, I think we'll just talk about this tomorrow, really. On 2, they're going to give us what the integral of f equals, the integral of g equals, and the integral of h equals. And we're going to practice using these properties. But I'll just pause there, and we'll talk about that tomorrow. It only leaves us with 2.5 pages for tomorrow.